Good afternoon. So today, my name is Gomez Fonseca, and I will be giving an introduction to low-density parity check codes. And every talk about LDPC codes is usually a little bit different. So my proposal for today's talk is I'm going to start giving like the basic definitions about coding theory. And then I'm going to introduce LDPC codes. I'm going to mention a little bit of the decoding is going to be very superficially, very brief, and then I'm going to switch to the discussion of some construction strategies for LDPC codes. So let us start to talk about the basics of coding theory. I'm going to let FQ be a finite field with Q elements, and an NK linear code is just a k-dimensional subspace of FQ to the n. And these parameters n and k are called the block length and the dimension of the linear code respectively, and C, the elements of the code are called code words. Okay? And there are two simple ways to represent a code. The first one is via a generator matrix, which is just a matrix whose row span is the linear code C. Any matrix that satisfies this property then is going to be called a generator matrix. And the other way to represent a code is via the null space of a matrix that we called the parity check matrix of the code. And this is a matrix that satisfies the property that HC transpose is equal to 0 transpose, and all the elements in the code can be represented in this way. Okay, so this is a parity check matrix. And when we talk about LDPC codes, parity check matrices are important. Okay. Now, the Hamming distance is another important concept. So if you have two vectors, x and y in FQ to the n, then the number of positions in which they differ is called the Hamming distance between the two vectors. And the minimum of all of those possible Hamming distances is called the minimum distance. So if a code C has minimum distance d, then we say that C is an NKD linear code. And the minimum distance of a code determines its error correction and error detection capabilities, so we want linear codes with large minimum distance. Now, that's the basics about coding theory that I wanted to mention. Now we can switch to talk about LDPC codes. And LDPC codes were invented by Gallagher in the 1960s in his PhD thesis, and he developed this class of error correcting codes that later were proved to be capacity approaching. And the problem with these LDPC codes at the time of the discovery, they were impractical to implement because we didn't have the technology to work with them. So they were largely forgotten and reinvented several times for the next 3 decades until the late 1990s, when they gained the attention of the research community again. And they have been a major research topic since then. Okay? Now, the capacity approaching performance of many members of this class have made it suitable for applications such as deep space communication, satellite communication, wireless, and even cellular communication. And there are different strategies that can be used to construct an LDPC code. So I'm going to focus on random and algebraic construction strategies. So what is an LDPC code? An LDPC code is just a linear code that satisfies the property that it has a parity check matrix that is sparse in its non-zero entries. Okay? And in this talk, I will be talking about binary code. So basically, this means this guy is sparse in the number of entries equals to 1. So most of these entries are going to be equal to 0, and some of them are going to be equals to 1. But LDPC really refers to a representation of a code instead of the code itself, because a code may have one representation that it has low density, but another representation that doesn't have low density. And the word low is a vague term because if you read papers about LDPC code, depending on the paper, they specify like a density. And usually LDPC refers to where the rows has a number of ones that is at most the square root of the block length of the code. But you can have, I don't know, a paper that says, well, density for us is less than 5% or less than 10%. It depends on the application also. If you specify the condition that every column has j ones and every row has R ones, then this is what we call a JR regular LDPC code. And in the case, if this is not the case, then we're going to say that this LDPC code is irregular. And low density means that J is way smaller than the number of rows, and R is way smaller than the number of columns in that parity check matrix. Gallagher, in his PhD thesis, proposed an ensemble of LDPC codes. So if you take 3 parameters, n for the block length, J for the number of ones in each one of the columns, and R for the number of ones in each one of the rows, he defined this family of m by n parity check matrices H, where m satisfies this equation. So m is equals to n times J divided by R. And the way he proposed this ensemble is, well, if you want to construct this LDPC code that has J ones in every column and R ones in every row, you can start by making the first R entries in the first column, all of them equals to 1, and the rest of the coordinates are 0. And then for the second row, the first R entries are 0, and the second R entries are equals to 1. And you continue in that fashion until the last R positions are equals to 1. And this is going to give you the first, you can think about it as a row block. Now, to construct the other row blocks, you're going to choose a permutation of all the columns in this row block, and that's going to be your P2. Your P3 is going to be another permutation of your row block, and so on. And you're going to have J of these row blocks, okay? So this is the Gallagher ensemble. And something that he proved in his PhD thesis is that if you pick one of these codes at random, it is asymptotically good with high probability. And that means that the minimum distance of these codes grows linearly with the block length, and also the design rate of the code is bounded away from 0 when you increase the block length. So this is what we mean by asymptotically good. So every time you talk about LDPC codes, it is impossible not to talk about a graphical representation of these codes. And that's done by defining what we call a Tanner graph. The Tanner graph was a strategy, a construction strategy proposed by Michael Tanner in this paper in 1981, where he proposed a way to construct these LDPC codes using graphs, and also other ways to generalize the constraints that should be satisfied by these linear codes. So consequently, every time we talk about the representation of linear codes in a graph, we talk about Tanner graphs. Okay? So let us explore how this works. If you have an LDPC code with parity check matrix H, with entries Hij, we can construct a bipartite graph G that we're going to call the Tanner graph in the following way. So you have 2 sets of vertices, Vs and Vc, and they are disjoint, okay? There are no 2 vertices that belong to both of these sets. And the elements in Vs are called variable nodes or symbol nodes, and there is 1 symbol node per each one of the columns of your parity check matrix. And the elements in Vc are called check nodes or constraint nodes, and you have 1 per each one of the rows of the parity check matrix. And you are going to connect a symbol node Sj with a check node Ci if and only if the entry Hij is non-zero in the parity check matrix. And in this case, we're working with binary LDPC codes, so the entries of this matrix are zeros or ones. So here's an example of the parity check matrix of an LDPC code. This guy has 2 ones in each one of the columns and 3 ones in each one of the rows. So this is a 2-3 regular LDPC code. And if you notice, most of these entries are 0 and only a few of them are ones. So this is an LDPC code. Well, the null space of this guy is an LDPC code. And if you talk about the graph, well, this is how the Tanner graph looks like. So if you see, there are 8 check nodes, 1 per each one of the rows, and there are 12 symbol nodes, 1 per each one of the columns. And they are connected in such a way that, for example, in the first column that corresponds to the first symbol node, the first symbol node is connected to the first check node, and the 5th check node. So if you go to the graph, symbol node S1 is connected to C1 and C5. And you continue constructing the edges in this way. Now, when we talk about LDPC codes, each one of these rows corresponds to a constraint. And that constraint is given by, if you let the symbol nodes Sj denote just a variable, think about Sj now as a variable, the summation of all of these Sj has to be equal to 0 modulo 2 when Hij is equal to 1. And this is for the constraint node Ci. So in our previous example, in this Tanner graph, there are 8 constraints. So we have 8 check nodes, so we have 8 constraints. And a binary vector x equals to x1, x2, up to xn is going to be a code word or an element of our code if and only if all of these constraints are satisfied when you replace Sj with the coordinate xj in that binary vector. Now, while a parity check matrix of a Tanner graph represents a unique code, a code can have multiple parity check matrices and multiple Tanner graphs. So when we talk about graphs, it is important to talk about some substructures in the graph that later I will tell you that are problematic substructures, like for example, cycles. So a walk, if you talk about a walk of length m, this is just an alternating sequence of vertices and edges that look like this. And if you impose a condition that the first vertex v0 is equal to the last vertex vm, that's what we call a closed walk. And if all the vertices in here and all the edges are distinct, that's what we call a cycle. And if there are k edges in this alternating sequence of vertices and edges, then that's what we call a k-cycle. And the length of a shortest cycle is called the girth of the Tanner graph. Okay? So we're interested in cycles and girth when talking about LDPC codes. So this is an example of a tiny Tanner graph. It has 2 check nodes, 3 symbol nodes, and the guy in purple is a cycle of length 4. This graph has girth 4. And then this other one, which is the one I presented to you before, it has girth 8, and I'm showing you here a cycle of length 8. Okay? Is there any questions so far? No? Okay. The codes, the LDPC codes that I have mentioned so far are usually referred to simple LDPC codes. And the reason is because the constraint that should be satisfied corresponds to the codes that we call simple LDPC codes. So we can generalize those requirements, those constraints in the following way. So if you start with a sparse bipartite graph as before, and that's our Tanner graph, you can impose a condition that each one of those constraints are now more specific linear codes of a specific block length R. So suppose that the row that you are considering right now has R1s. You are going to pick a linear code that has block length R, and now those specific coordinates, when you replace Sj with Xi, with Xa in the previous case, that has to be a code word of the linear code that you chose. And I'm going to mention an example so that it makes more sense. So this is the Tanner graph that I presented before, but now we're going to generalize this LDPC code. So this incidence matrix was the parity check matrix of the simple LDPC code, but now I want to choose a different linear code for each one of these rows. So we're going to generalize this guy. If we generalized these constraints, this is no longer the parity check matrix of our code. Now, before, the constraint C1 was given by this summation, and it has to be equal to 0 modulo 2. So we have S1, S5, and X9. So the first, the fifth, and the 9 coordinates are going to give you a vector, a binary vector of length 3. So you have to choose a linear code that has block length 3. And I chose one that has this parity check matrix, the 1, 1, 0, 0, 1, 1. And now that vector S1, S5, and S9 has to be a code word of this lettering code. So now instead of having this constraint, we have these two equations and they have to be satisfied. So now we have S1 plus S5 has to be equal to 0 modulo 2, and S5 plus S9 has to be equal to 0 modulo 2. And we're going to choose a linear code per each one of the rows in this incidence matrix of the Tanner graph. Okay? So there are a few comments that I want to make when we talk about generalized LDPC codes. The overall constraints, you have more, overall, you have more constraints that should be satisfied. And that makes the rate to decrease. So the rate, which is the quotient between the dimension and the block length of the code, is typically smaller when you compare a simple LDPC code with a generalized one. And the incident matrix, as I said, is no longer the parity check matrix of your code. I'm going to switch to talk about decoding. I'm going to do that very briefly because I'm more interested in talking about constructions. So the class of decoding algorithms that are used for LDPC codes are collectively termed as message passing. And the reason is because the operations can be explained by passing messages along the edges. And each one of the nodes or each one of the vertices work in isolation. And they are going to receive information, there is information incoming from the neighbors. And only the neighbors. They don't have access to information coming from other vertices that are not connected to them. And they are also known as iterative decoding algorithms because these messages that are passing back and forward between the symbol nodes and the check nodes, this is done iteratively. And this is done until we achieve a result. Basically, if we say, yes, this is a code word, or the process is halted because we haven't reached a result, okay? That's after we have completed a specific number of iterations. Now, each one of these message passing algorithms are named depending on what kind of messages are being passed along the edges. For example, if you think about the bit flipping decoding algorithm, the messages that you are transmitting from one node to another ones are bits. So that's why it's called bit flipping. You're going to change 1, 0 to a 1 and 1, 1 to a 0 and so on. And if you think about belief propagation decoding algorithm, the messages that are transmitted along the edges are probabilities and they represent some level of belief about the value of a code word bit. Okay? Now, I'm not going to go into details about the decoding strategies, but I wanted to mention how the decoding works. In the case of generalized LDPC code, something what we can do is to do the belief propagation in the constraint graph. But then when you think about the constraint nodes, you use other type of decoding, like for example, maximum likelihood or belief propagation. You can choose your favorite decoding algorithm. And that's going to give you some trade-offs between performance and complexity. And you can play with those two conditions. Now, there's a problem when you do decoding on an LDPC code. And the reason is because there are some structures in the graph that affect the decoder. And basically, usually these message passing decoding algorithms assume that the information that is incoming from one node to another one has been done independently, okay? Now, the girth is going to determine the number of iterations for which the messages are propagated independently. So once the informations have transmitted exactly the number of edges that corresponds to the girth, now the messages are no longer independent, so you are introducing correlation and that affects the performance of the decoder. So short cycles are usually considered to be bad, and we want to avoid constructing something that has short cycles. And much of the research has focused on designing these codes with larger girth because this is a way to prevent bad information from being pass from one check node to a symbol node and vice versa. So now that's what I wanted to say about decoding. I'm going to talk about constructions now. So there are two ways, there are many ways to construct LDPC codes, but one is using random strategies. Like for example, I can choose randomly where I want to place the ones in my parity check matrix. And the problem with doing random constructions, and I say problem, but it depends what you want, you lose efficient representation when you are randomly deciding where you want to put the ones. The analysis is no longer simple, and the encoding is not that easy, right? Because you're choosing randomly when you want to put the ones. But the good thing about random codes is that they perform very well. Now, one of the most important construction strategies for random LDPC code is called this progressive edge growth algorithm. And that's the only random construction that I'm going to talk about today. And I'm going to talk about algebraic constructions. To understand how the PEG algorithm works, we need to understand how a subgraph is expanded from a symbol node. So I'm going to choose some symbol node as J, and I am going to identify all the check nodes that are connected to SJ. And this first layer is what we call depth 0 in the PEG algorithm. Now, I'm going to take each one of these check nodes and I'm going to compute to identify all the symbol nodes that are connected to them. Like for example, this guy, well, all of these are the symbol nodes connected to this guy, but I am going to only choose only those symbol nodes that are not equal to SJ. And I'm going to continue in this way. Well, this is depth 1. I'm going to choose all the check nodes that are connected to each one of the symbol nodes that do not appear in a layer before. Okay, this check node doesn't appear in this layer. And I'm going to continue in this fashion until the maximum depth L. Okay? The collection of all the check nodes appearing in this subgraph expanded from symbol node SJ is what we call NSJL. Okay? That's the neighborhood of this symbol node. So this progressive edge growth algorithm is a suboptimal tool that is used to construct the tangent of LDPC codes that they have large girth. That's the goal of this algorithm. And for each one of these symbol nodes SJ, what you're going to do is to define a local girth, GSJ, which is the length of a shortest cycle that is passing through each one of these symbol nodes SJ. And then at the end, when you finish the construction, the girth of your LDPC code is going to be the minimum of all of those local girths. Now, in this algorithm, the local girth of a symbol node is maximized. That's the goal of the algorithm, is to try to avoid the construction of cycles. And basically, you are going to place a 1 in your parity check matrix in a position where you, first of all, delay the creation of cycles. But if you are forced to create cycles, something that you can do is to create the smallest possible number of cycles when you are placing that 1. When you're placing a 1, there are 3 cases that we have to consider. The first case is when you start with a symbol node SJ, and this guy is not connected to anything. So you can choose from all the possible check nodes in your tangent graph, 1 at random, so that's why this is a random construction. You choose, let's say, CI, and you are now in depth 0, but the creation of this edge doesn't create any cycles. Okay? That's the first case. The second case is when, okay, you have expanded a subgraph from the symbol node SJ, but there are check nodes that are not present in this expanded subgraph. So you're going to choose 1 at random, and you're going to create an edge, and this is depth 0 again. So the creation of this edge doesn't create any cycles. And the third case is when you have expanded a subgraph and SJ is somehow connected to everyone of the check nodes in your Tanner graph. So now you are forced to choose one that is as far as possible in the tree. So you're going to pick, let's say, this guy. This is CI, and you're going to make an edge back to SJ, and this guy forces the creation of a cycle. So the point of the algorithm is to delay the creation of cycles in this way. So as I said, all of this corresponds to placing ones in your, you start with an empty zero or all zero parity check matrix, and you start placing the ones in a position where you avoid creating cycles or delaying the process of creating cycles. The other strategy is an algebraic strategy, construction strategy, and this one is about taking a graph cover of a relatively small bipartite graph that we call the product graph. And that graph cover of the product graph is what we take as the Tanner graph of our LDPC code. And the incidence matrix of this Tanner graph is the parity check matrix of the LDPC code. So let me describe how this works. I'm going to start with a bipartite graph G. G is usually small, maybe 2 check nodes, 3 variable nodes, or 4 check nodes, 5 variable nodes. It's a relatively small product graph. And then I'm going to pick a number n that is a positive integer. I am going to do the following. For each one of the vertices in the graph, let's say v, I am going to create n copies of this vertex v, and I'm going to denote them by v tilde l, where l between 0 and that number n is minus 1. For each one of the edges, I am going to first assign a permutation sigma on n elements. Sigma is a map from the integers modulo n to the integers modulo n. And again, one permutation per each one of these edges. And once I choose a permutation sigma, I am going to create n copies of this edge, and I'm going to denote them by e tilde l. Okay? Now, how I'm going to connect the vertices in the graph cover? I'm going to first, once I create these e tilde l copies of that, I'm going to join the u tilde l with v tilde sigma of l. So I'm going to map the lth copy of u to the sigma lth copy of v. And that's going to give me a cluster or a cloud of those edges and vertices. And if you set v tilde to be the collection of all of those v tilde l for v in v and l between 0 and n minus 1, and you do the same for the edges, this is a graph that is a graph cover, and we call it the Tanner graph of our product graph, of our LDPC code. So this is an n-fold graph cover, as I said, a lifting factor, and then this idea of assigning a permutation to each one of these edges, that goes back to the 70s, where Gross and Tucker were studying the construction of covering spaces using graphs. And they have a very interesting book about a topological graph theory, where they have a chapter that is about constructing graph covers and how you assign permutations to each one of these edges, in case you are interested. This was using this graph cover idea, but we can describe this process algebraically. And what we're going to do is to let this matrix B be the incidence matrix of my product graph. Let's say that we have NC rows and NV columns, and each one of these entries Bij is a non-negative integer. So they can be either 0 or a positive number. And to construct the incidence matrix of the Tanner graph, I am going to replace each one of these entries Bij with a summation of Bij permutation matrices of size n by n, where this n is the degree of the graph cover that I mentioned before. And if this entry Bij is equal to 0, then I'm going to replace that entry Bij with an n by n all 0 matrix. So the null space of this matrix H is a protograph-based code, and this is called the parity check matrix. And if most of the entries in this matrix are 0, then the null space of this matrix is an LDPC code. So something that you can think about is that maybe this matrix, this incidence matrix of the graph, has entries that are larger than 1, so that represents multiple edges in the protograph. But what we usually do when talking about protograph-based codes is that I'm going to choose those permutations carefully such that in the graph cover, I no longer retain any multiple edges. Because again, multiple edges represents short cycles, and short cycles are bad. Okay? So this is an example. If I have the 2x3 all ones protograph, this is the incidence matrix of the protograph, I can replace each one of these entries, a Bij, with only one permutation matrix of size 4x4. So I chose this one. You have identity, 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 identity here, and then some other permutation matrices. And in the graph representation, this is how the protograph looked like. So I included this graph in a previous example. So this was a protograph. And then this is how the Tanner graph looked like. That is a graph cover of this protograph. Okay, so now you can choose specific permutation matrices to do this graph cover. And what I'm going to do is to first impose some conditions on the parameters. I will impose a condition that the number of columns in the protograph is NV, is an odd prime. We usually have at least the same number of columns as rows. This lifting factor n is going to be equal to exactly the same number of columns. The entries of Bij are equal to 1. And I'm going to set Hij to be equal to sigma to the I times j, where sigma is going to be this n by n permutation matrix. And this matrix is just, you take the identity matrix, and the first row, the first column, you're going to place it at the end. Okay, so now we're going to take powers of this matrix sigma. And there's a family of codes that is called array-based LDPC codes that has parity check matrix defined in this way. So you have a row of identity matrices, a column of identity matrix here, and then you have sigma, sigma square, sigma cube, up to sigma to the nv minus 1. And then the exponents in this third row are 2 times the exponents here, and then you continue in that way. And this is called an array-based LDPC codes, and these codes satisfy the property that the girth is not usually small, okay? So this code was introduced by Fan in the 2000s, and this is a protograph-based LDPC code. Another way to choose the permutation matrices in this graph cover is by imposing a little bit of different conditions here. So I'm going to set n be a prime number, and a and b are going to be 2 elements that are non-zero in Fn, which is a finite field. And I'm going to assume that the multiplicative orders of a and b are now m and n, and I'm going to construct a parity check matrix of a code in the following way. So I'm going to take sigma, sigma to the a, sigma a squared, and up to a to the m minus 1. And now the exponents in the second column are going to be the exponents in the first column times b. So it is 1 times b, b, a times b, ab, a squared times b, a squared b, and so on. And then the exponents in the third row are going to be these guys times b squared. And then the fourth row column are going to be these guys times b cubed, and so on, until the last column where you multiply all of them by b to the n minus 1. And the exponents in this case are taking modulo, computed modulo, that lifting factor n. So these codes were introduced also in the early 2000s, and they are called TSF codes. Now there is an example, like a very famous TSF code that has the following parameters: 155 for the block length, 64 for the dimension, and minimum distance 20, which is relatively large for these two parameters. And this is how you you construct the parity check matrix of this code. So it has lifting factor n is equals to 39, A and B are chosen to be 5 and 2. M is the multiplicative order of 5 in here, and n minus 1 equals to 30. And this n is the multiplicative order of 2 in 30. Now, all of the codes that I have mentioned before, all the protograph ones, the array-based and the TSF ones, all of them are members of a broader class of LDPC codes that are called quasi-cyclic LDPC codes. And these guys constitute a subclass of codes, LDPC codes, that enjoy of significant relevance because they can be described very compactly, and they have both efficient encoding and decoding. So that's why quasi-cyclic LDPC codes are attractive for implementation purposes. And they have motivated researchers to propose like a wide range of construction strategies. So these are some of the reasons why quasi-cyclic LDPC codes are now present in many standards, including those developed by CCSDS. So this is the Consultative Committee for Space Data System. NASA is a member of this committee. And then you can also use quasi-cyclic LDPC codes for deep space communication, cellular communication, and wireless communication, including Wi-Fi. And to give you an idea how this construction works, in that process of replacing the entries Bij of your protograph with permutation matrices, now you're going to impose the condition that those matrices are circulant. And an n by n circular matrix is just a matrix where you have the first row, and the second row is going to be the same row, but cyclically shifted one position either to the left or to the right. And then you continue constructing the rows in that way, circularly shifting by one position either to the left or to the right, the previous one. So now these matrices are circulant permutation matrices. And for my PhD thesis, I work on quasi-cyclic LDPC code, and I proposed a variety of projects that take into account different projects on, for example, the girth and cycle analysis, where we presented, for example, necessary and sufficient conditions that should be satisfied in order to guarantee a specific girth. I studied the cycle distribution of quasi-cyclic LDPC code, proposed efficient strategies to count cycles. And I also work on the construction strategies, for example, of generator matrices, given a parity check matrix of an LDPC code that is quasi-cyclic, how you can construct a generator matrix using certain substructures in the matrix. I propose some construction strategies using partial orthomorphism, some low complexity PEG algorithm. These are also efficient algorithms to construct quasi-cyclic LDPC codes using both a random and an algebraic approach. And then another strategy using the Hermit-normal form of a matrix that you can construct from some cycles in the Tanner graph. And I also work a little bit on the generalization of some quasi-cyclic LDPC codes to now generalized quasi-cyclic LDPC codes. I have more to present, but maybe I can stop here. Thank you so much for your attention. Yes.
I want to know, since understood, one sort of objective is to try to avoid cycles of short length.
Yes.
Are there any constructions of LDPC codes that are inspired by ideas in design theory or geometric ideas where you use certain, I know like for very simple avoiding triangles, which is like the cycle of length tree, right?
Yes.
You can use certain geometric ideas from finite geometry to sort of ensure that you can do that. Are there like any sort of more sophisticated examples of that in the literature? Like,
Well, I'm not very familiar with geometric constructions, but I know there are some of them. That, like for example, the one you were mentioning about triangles, avoiding triangles. But in this case, since the graphs are bipartite, you will never have triangles.
yeah, of course.
But yes, there are some constructions that involve geometry, but I'm not familiar with them. Yes, thanks.
I have a question.
Hmm?
What's an orthomorphism?
That's a permutation matrix that satisfies the prop. If you have a map X, let's say a map f of x, maybe. So I can impose a condition that if this is a permutation matrix, well, a permutation on a specific number of elements, this guy is also a permutation. So this is what we call a partial orthomorphism.
Connected to a square.
Yes. Yes. Yeah.
So that's a standard name?
Yeah.
Orthomorphism, yes. Mhm. Yeah.
Anything else?
Thank you so much.